Alright, let's discuss how to find the image location in a curved mirror using a graphical method. There are really three ways you can find the image. You could do it experimentally, you could do it mathematically, and you could also do it graphically. So you'll need to know for the test how to do it graphically and mathematically. Alright, so we have over here a curved mirror that is shown. This is a concave mirror, and then we have another example here which is a convex mirror. In essence, you really only need just two rays to find the image, because you need to find an intersection of two rays, say ray 1 here and ray maybe 4, and then you could find this image. This little red arrow that you see here is an image. Okay, so let's start off of how we construct the rays. They're in a mirror. You're fortunate enough to find you could actually draw an infinite amount of rays, but there are 4 convenient rays that you can draw. You need at minimum 2 when you do a test or a quiz. All right, I suggest that you know 3 of them in case you forget one of them at least. All right. So what you first do is normally you would be given a curved surface like this, and then the principal axes would be labeled, and then usually a focal point would be labeled. Kind of something like, if I were to skip ahead in some of the problems, something like this in example 3 that you'll see later after this video. So you'll be usually given the mirror, and then the object, and then the axes, and then normally the point F. Sometimes they may or may not give you the center curvature. They'll tell you it's a spherical mirror, and you got to know, well, this is going to be twice this distance in here, because we know that the radius of curvature is twice the focal length. Okay, so how do we construct these rays? Let's start off with ray 1. Ray 1, you first draw your object. So we normally draw, an arrow. So this represents the object here, by the way. So we draw an arrow. You could do it whatever size you want. I chose this size here, and then we take your ruler and you line up your ruler right along here. Alright, so it's parallel to the principal axis. So put your ruler along here and you trace out a line until this is like the incoming beam of light. I call this the incident beam. And then when it gets to this mirror, remember it's obeying the law of reflection. So if you were to draw like a normal line in here, you don't have to do this at all, but you would see that this angle of incidence must be equal to the angle of reflection. But you don't have to do that, all right? You don't have to draw the normal. We happen to know that any parallel ray to the principal axis will reflect through the focus. So the reflected beam will go through F. So that's ray 1. Ray 2 is kind of like the opposite of ray 1. What we do is we send a ray from the top of the object. So all these beams of light are coming from different angles, right? So they go from the top of the object, takes a different path. Now it goes through this focus F first. And then, so it's kind of like the reverse idea of ray 1. Goes through F, and then when it hits the mirror, again, it's obeying the law of reflection, so the angle of incidence equals the angle of reflection. And so this beam will now reflect parallel to this principal axis. So you line up your ruler to F, you draw a line straight through here, and then you draw a line parallel to the principal axis. That's ray 2. And then you have enough to find the image at this point. But let's continue. We have now ray 3, a good checking point. Any ray that goes, now this ray happens to go right through the center curvature. It's really, if it goes through the center curvature and continues along through the mirror, to the mirror, it's actually traveling along the radius of that circle. And you know the radius of a circle is going to meet tangent to the surface. So it's going to meet at an angle of 90 degrees. So it's going to reflect right back onto itself and come back and kind of shoot off this way, for example. Okay, so that's ray 3. Ray 4 is not seen so much in many textbooks, but you could draw it. It's a ray that would go from the top of the object and then come in, hit right at the vertex, right in the middle of the mirror, and then this angle in here is equal to this angle here. All right, and so reflect. Now, I guess you need a protractor. You don't really need to. You could just measure this height and then make sure when this beam comes over here, it's the same as this height over here. Now, if you notice, all of these incoming beams are going this way. You have to, by the way, have arrows on all of your beams of light because you have to need to tell us what direction that light is going. And you can see they're all leaving and going this way as well. Okay, this one has kind of two arrows going on it on top of itself, right? But if you see all these beams, they all come back and they meet. They all intersect at this point. So that means the light actually will intersect here and form an image. So now because this point happens to fall below the principal axis, that means the top of the object is upside, it's like basically the object is upside down. The image is upside down. So now that top of the object is here. And so it's going to, and you have to have that, if you were drawing light from here, you're getting kind of over here. So eventually you get this image that forms right here. It's upside down. Now, you should be able to describe three characteristics of the image. You need to be able to talk about its nature. Is it real or virtual? You have to talk about its size. Is it smaller, larger, or the same size as the original object? By the way, this is the image, right? And also, you need to talk about the orientation. Is it inverted or is it still upright? So, those are the three characteristics that you need to discuss. You could see, first of all, it's real. Why is it real? Because these light rays actually form at this particular location. They actually do really intersect here. If you were to put a screen right there, you're actually going to get a real image. All right? And I'll show you that in class. So, it's real. This image is real. If you measure the height here and measure this height, you can see it's smaller. So it's a smaller image, smaller than the object. And then lastly, you can see the orientation has been flipped over to the other side, so it's inverted or upside down. Okay, so these are the sort of three characteristics of the image. Okay, so this is one of the types of images. Now you can get a variety of types. You can move this object around to different locations and you get different types of images. And you'll see that in example 3 as you follow through that example. The next thing is we have a convex mirror, just to kind of go over this in general. Kind of the same principles, but a little bit different. So we have the object here, again, in front of this curved surface. So this is the darkened side of this back of the mirror here. And the light is coming in here parallel to the principal axis. Now, it's not going to reflect towards here because it's not converging, it's diverging. So it's got to diverge away, and it diverges away from this focus. Now, you do not put a solid line in there. It has to be dashed in here because the light doesn't actually come through the mirror, right? So your eyeball right over here, this is say your eye would be seeing this beam of light, this reflected light, and it would be thinking this light is coming from over here. Right? It's going to think that light's going in a straight line. But of course, you're not going to draw a solid line back here because it's actually not really passing through the mirror. So that's ray 1, parallel, and then diverges away from the focus. Kind of like this, parallel, but goes towards it. This one's parallel and goes away from the focus. Ray 2, a little bit trickier. Ray 2 was going through the focus and then parallel. Same idea. You kind of have to line up your ruler between the top of this object to F. Line up your ruler here, and then you trace your line right along until you get to the mirror. Stop, because it can't go through the mirror. Now they've drawn a dashed line in here. You probably should erase that because that's just there to kind of guide you where this ray is coming in. And then when it hits the mirror, it's going to reflect parallel to the principal axis, kind of like this one. Here it went to the mirror and then went parallel to the principal axis. So it goes parallel to the principal axis. Now your eyeball here will be looking at this and looking back and thinking the light is emanating from behind here. So you draw a dashed line. So you're always dashing back the reflected part of the beam. Okay, so this is dashed back here and this is dashed here, and now you have enough to figure out where the image is. But let's continue. Number 3, usually the easiest one here because it goes towards the center of curvature here, and it's going to strike the mirror at 90 degrees, so it's going to just come back onto itself and reflect back way. So your eye, as it looks at this light here, it's going to think that the light goes in a straight line coming from way back here. So in forming an image right here. Last, number 4. Again, not very common, but you can draw the light coming towards the vertex or the center of the mirror. And then if you measure this distance and then measure this distance here, the reflected beam will come back obeying that law of reflection, so that this angle of incidence equals this angle of reflection. And then if you look with your eye and dash back the reflected beam backwards, you're going to see this is the image. So that is the image. Now, you need to describe this image. Characteristics of this image. Is it real or virtual? So ask yourself, can you put this on a screen? Or more importantly, do these light rays actually really do intersect? Do they actually go through the mirror and form an image right there? No, they don't. So this is actually virtual, because the light rays are formed with dotted lines. So if this image is formed with dotted lines, it's not real, it's virtual. Okay, if you look at the size of the image compared to the object, is it smaller, larger, the same size? No, it looks like it's smaller. So this is a smaller image, right? Look at the height of that, look at the height of that smaller image. And lastly, is it inverted like this image, or is it upright? It's upright, right? You can see some people call it erect. It's your choice. All right, so that's it. You should now go on to practice the ray diagrams. Actually, before I set you loose on that, go down to the bottom here. This is probably important. This is the math part now, just to kind of tie this in here so you understand the equations and so forth. We introduced this earlier. So this is the relationship between the focal length and the radius of curvature. So I'll just label this on the diagram. This is R in here. And the focal length is the distance between the focus and the vertex. And there's the focal length. And then we also have this equation. All right, and this is a very important equation that you're going to be using to solve problems. Okay, it's pretty straightforward to use. SO stands for the object distance. SI stands for the image distance. Let me label those on the diagram here for you. So the object distance is the distance from the object here all the way to the mirror. So this is S sub O for object distance. And my diagram is getting a little bit cluttered, but the image distance is the distance between the image and the mirror. So this would be this distance right here. Okay? I'm going to label that as S sub I for image distance. So now you know how you can check it out. So after you finish the ray diagram, you can actually measure this out with your rulers and see if it actually comes out with what you get mathematically. And then one more equation here, and that's the magnification. And the magnification we said earlier is the ratio of the image height to the object height, and it's also equal to the negative of the image distance to the object distance. Let's just take a look at up here just to kind of label the distances here and kind of distinguish between when the image is in front or behind and how to treat the signs. This is SO for object distance, the distance from the object to the middle of the mirror. This is SI for the image distance, but it falls behind the mirror. And because it falls behind the mirror, that value is going to be negative. And then we have the focal length, which is the distance between the focus and the center of the mirror. And that focal length is negative as well because it falls behind the mirror. So that's one of our sign conventions I'll mention in a minute. And there's the radius of curvature between the mirror and C. And once again, that's also negative because because it's behind the mirror. I also forgot to mention one other thing too. The height of the object. So you measure this distance right here, and that would be the object height. I'll label that as H sub O. And similarly over here, we have the image height, which I've labeled H sub I. Okay, and so here's your kind of key ideas with the sign convention. If the object's placed in front of the mirror, which is normally what we do, we'll have a real object. Now, it's possible to get a virtual object, but we'll get into that later on when we do an image of an image. You know, when we do find an image for the first mirror and then we pick another mirror in front of it. We'll talk about that a little later on once we get a handle of that. Normally, I'll introduce that once we do lenses. If the object was behind the mirror, it would be a virtual object. I'll leave that to later on. The image. If the image distance, when you calculate it, comes out to be a positive answer, that's your indication that's a real image, and it's going to be forming in front of the mirror. If the image distance comes out to be a negative value, then it's forming behind the mirror, and that's your indication that it's a virtual image. So when you do the mathematics and you solve for SI, if SI comes out to be a positive value, you know it's real. If it comes out to be a negative value, then you know it's forming behind the mirror, and therefore it's a virtual image. So your test mathematically to tell whether it's a real or virtual image is whether the image distance is positive or negative. Okay, now, depending on the type of mirror, if you have a concave mirror that caves inwards, right, that's a converging mirror, that focal length is going to be, the focus is going to be in front of it. So the focal length and the radius of curvature are both positive. If you have a convex mirror where the rays are going to diverge away from it, then you have a focal length and a radius of curvature that is negative. Also, if the magnification turns out to be positive, then the image is upright. If the magnification turns out to be negative value, then it's an inverted image. All right. If m is less than 1, it's a smaller image. If m is greater than 1, then it's larger. And if m is equal to 1, then it's the same size. Okay, I put absolute value signs because I just want to know the magnitude of it, right? We know whether it's inverted or upright by the sign. If it's a negative m, that's inverted. If it's a positive m, it's upright. Okay, so now you should have an idea of how to tackle problems both graphically. You have to know both. You have to be able to construct the ray diagram and then be able to check your answers with the mathematics. Okay, go ahead and do examples 3 and 4 now.